We are in Math 1, Integrated Math 1, Lesson 8-1, Exponential Functions. We are in our exponential unit. Let's dive straight into tables. Typically speaking, there are three main mathematical representations for any sort of math function. You have a table, a graph, and an equation. Knowing how all three of those work and how they're interrelated is what makes you good at math. So let's start with what I consider to be the easiest part. Tables. We dealt with that when we were trying to do our folding paper to the moon. So a little bit of a lack of basis there, but I will show you what's going on here. Normally when we have a function, you'll have inputs that just go up by 1. These are all the same inputs, but the outputs, the y values, will be different in all of these. I need a quiet raised hand here to tell me what is going on with my y values to get from 1 to 2, to get from 2 to 3, to get from 3 to 4, and 4 to 5. What operation am I doing when? You're just adding 1. Whenever you're constantly adding with the y's, that has a very specific type of function. It is not exponential. It's an old one that we learned. Does anyone know it with a quiet raised hand? This is what's known as a linear function. A linear function constantly adds over and over again. You go right one, up 1, right one, up 1, right one, up 1, because you're adding 1 to the heights. An exponential function will not add. What did we do with our folding paper? We multiplied every single time. Watch this. To get from 1 to 2, to get from 2 to 4, 4 to 8, and 8 to 16, you're multiplying, typically speaking, by the same number over and over. If it's a real world problem, it'll be like 1.9, 2.1, 2, 1.9, somewhere in the general vicinity. But with math, math is in our minds. Math is perfect. This is math. This is perfect. I'm going to be multiplying by 2, multiplying by 2, multiplying by 2, multiplying by 2. This is exponential. And as we saw, these are scary. Do you guys remember how many times did you need to fold a single sheet of paper until it reached the moon?
42.
42 times, and it reaches the moon. And the moon is very far away. As I told you, you can fit every single planet in our solar system between the Earth and the moon. That's how far away the moon is. It's crazy far. All right. So, and a lot of students will say, well, to get from 9 to 3 and 3 to 1, I divide by 3. And you are right. But typically speaking, my definition for an exponential function is always multiply, which means I have to multiply by close, a fraction. Exactly. So Henry has it. In each of these cases, I'm multiplying by a third, multiplying by a third, multiplying by a third, and multiplying by a third. That is still known as an exponential function because I'm multiplying by something every single step. So you all nod our heads. We're good to go. We've seen this before, and it's easy. One is adding, that's linear. One is multiplying, that's exponential. We know the distinction between the two with a table. If I saw that on a problem on the homework, which we don't have in this class for this unit, then we would know what to do. So I want to graph one of these and see what it looks like because we have not seen that yet. So I'm going to graph 0, 1. So 0, 1 is this point right here. We all nod our heads. Did I do it correct? Don't graph 1, 0. It goes X, then Y. And then I'm going to graph 1, 2. So I'm going to come down here and graph 1, 2. And every single time that I move 1 to the right, 1 to the right, 1 to the right, the heights will be not added, but multiplied. And in this case, I chose 2. I could have been multiplied by 3 or 4 or 7 or 2.5. It doesn't matter. So if I multiply 2 by 2, 2 turns into a 4. Yeah, so we come up here and do a 4. And then the next height will be, shout out, 8. So I'm going to go to 3, 8. And then if I multiply by 2 again, you all shout out.
16.
Look at this thing. It's like almost off the chart. I make the chart super long for you guys so that it would stay on the chart. It goes and shoots off the chart. And that's a very characteristic example of an exponential function. They shoot off the chart really, really quickly. So I'm going to go ahead, and this is not a discrete function. A discrete function, again, is just a series of points. We're allowed to be continuous here. I'm allowed to connect this with a line. So I will do that. And it just shoots up off the graph. So now my question is, we know what happens on the right, but what happens on the left? Because if I go to the left, that corresponds to having a negative value, So if I go up here and I continue this pattern backwards, I can say, okay, if I go to 4 to 3, instead of multiplying by 2, I divide by 2. 16 to get to 8, I divide by 2. Constantly divide by 2, divide by 2, divide by 2. So if I have 1 here and I divide by 2, the height is, everyone shout out, 1 divided by 2 is? 1 divided by 2 is?
2?
1 divided by 2 is 1 divided by 2.
Oh.
1 divided by 2 is a half. So I'm going to come over here and I'm going to come to the height of a half. Oh, okay, I have a half. What's half of a half? A fourth. What's a half of a fourth? An eighth. What's a half of an eighth? A 16th.
How are you?
Will I ever get to 0? But I get really close to 0, right? I never hit 0, but I get close to 0, and that creates a new type of characteristic on a graph that you've never seen before. And I'm going to write that over here. This over here, it gets closer and closer and closer and closer to 0. If you look on Desmos, it looks like it touches 0, but if you zoom in and zoom in and zoom in, it never actually touches. And this is what's known as, and let me write this here, this is known as an asymptote. It's spelled weird. It has a silent P. Do you guys know how to spell pterodactyl? P. Yeah, exactly. There's a bunch of silent P's in English. I don't like it, but whatever. This is known as an asymptote. You pronounce it asymptote, but guess where the silent P goes?
Oh.
Right there. Randomly, I don't know why it's there. Don't say asymptote. It just, it sounds like you have a stutter. This is known as an asymptote with no P. An asymptote is a mathematical characteristic on a graph where you get closer and closer and closer to it, but you never touch it. There are some key examples where you can touch it, but I'm not going to talk about that in Math 1. We'll talk about that maybe in Math 3 or in pre-calculus. So this is a horizontal asymptote. In math, we sometimes have a vertical asymptote, but not in this unit. So technically, this is called a horizontal asymptote. And technically, the way that you're supposed to write that on your graph is you have a dashed line to say where is that magnetic force that's drawing you closer and closer, but you're not allowed to touch. I'm going to do a dashed line that is in blue down here. And I'm going to move this to, oh, that's not what I wanted to do. Let me grab no pictures here. If I move this line right here, that is the line of the asymptote, and it has an equation. Do you guys remember the equation of a flat line? Is it x equals or y equals? It's y equals. X equals is a vertical line, and y equals is a horizontal line. So this is going to be a y. Ooh, I don't want to do dash line. This is going to be known as a y equal to whatever height it was. What is our y coordinate? What does it pass through on the y-axis? Well, 1 is right here. 0 in this case. So y is equal to 0. And most commonly, exponential functions have y equals 0. But if you shift the function up, it's y equals 1. If you shift the function down 2, it's y equals -2. It's always going to be y equal to some number. It's always going to be a horizontal asymptote. So we have the graph down. It's weird that it has an asymptote on one side and shoots off to the charts on the other side, but that is a characteristic of a graph. So the domain, do you guys know what a domain is? Give me a fist of 5. How well do you know what a domain is? Like, how can you define what a domain is? If you want to explain domain to a kindergartner, how well could you explain it to a kindergartner on a fist of 5?
Like, I might explain range on accident.
Okay, try it. Let's see it. You gave me a 5. So give me one of them. And oh, you gave me a 4? Okay, Henry, you gave me a 5. Henry, you do domain.
So, domain,
I'm a kindergartner right now. Go.
the domain
Yes.
is how kindergartners know left and right.
Yeah.
I didn't.
The domain is how far the line goes right and left.
Yeah, I like that.
That's how
There's another way that you can define it for kindergartner. Can anyone else try it a different way? Yeah, it can be an annoying kindergartner, sure. I like that. Like, yeah, the Star Wars reference. How much left and right can you go? Another way that you can explain it is, what are you allowed to plug in? Sometimes you're not allowed to plug in things. For example, if I have the function 1 over x, am I allowed to plug in 0? No, because I would be divided by 0. So it's all the values that you're allowed to plug in. But graphically, Henry nailed the definition. It's how far left and right we're allowed to go. So on this graph, can I go left forever? Nod your heads, yes or no. It's a nod. This is a shake. This is a nod. A nod means yes. A shake means no. So yes, it goes to the left forever. But what about the right? No. Nod or shake? Go.
Oh, but yes.
Yes, you can. It just goes off the charts. You can go out here to 100. It just happens to be an answer that's like a bazillion, right? It's a huge number.
Will it ever go like straight?
That's a great question. Do you guys hear that?
Does it just keep going like?
Repeat it again. That was a great question. Everyone else needs to hear that question.
Will it ever go straight?
Is there ever a vertical asymptote is another way of asking that. And the answer is no. It never goes straight up unless you zoom in really far and you can't tell. If you zoom out and look at the forest through the trees, it continues to go right forever and ever and ever, which means the domain is, let me write the informal domain that you're not going to write. Don't use this. It's between negative infinity to infinity. Or you can just say it's all real numbers. We say all real numbers. This is the one that I want you guys to use. It's all real numbers. You're allowed to plug in anything you want.
It looks like that paragraph.
Yeah, it's like a paragraph.
So, okay. So whenever you have numbers and sets of numbers, we typically have what's called bold notation. So in this case, I have a bold R. If I had the time, the way that I'd really write my R is I'd go like this, and then I do this. Look how long it's taking me. And then I go like that. And now I have Team Rocket's logo. Okay, so a bold R is what I was trying to write there. But instead of doing that, it's much faster to just write 2 lines and make your R. Same thing happens with integers. Integers are whole numbers that are both positive and negative. Integers are a Z, but to make it bold, you just add another line and say a bold Z. Or if you want to talk about natural numbers or counting numbers like 1, 2, 3, 4, 5, then you can do a bold N. So here's a bold N. These are all sets of numbers. So this is the set of all real numbers. So I'll write a note on the notes. This means all real numbers. And you can start using this symbol now to say it's everything. And you can plug in anything you want.
I see it like the middle line makes an A with like the R and then it's like all.
That's how you memorize it? That's perfect. Okay, the range is a little bit different though. Can I go up forever and ever? Oh, sorry, I stole the definition. The range is how far up and down you're allowed to go on a graph. Can I go up forever? Yes. Can I go down forever? I can't go past 0. I can't even get to 0. So I cannot, for the range, I cannot go below 0, but I can go to infinity. So the range is all values between 0 and infinity. And this symbol right here versus this symbol right here are different symbols. A square bracket means you can be equal to 0. A parenthesis means you cannot be equal to 0. Can you ever be equal to infinity? No, that's why we have a parenthesis as opposed to a bracket. We do not have a bracket on 0 because we cannot touch 0. We're learning lots, right? Oh, by the way, the asymptote equation, I wrote up here, but let me write it down here. It's y equals 0. All right, so now let's talk. We've talked about a table, a graph, and finally, we're going to do an equation. So for an equation, I want to help build this to make sure that you get as much sense as possible.
I remember f of x. That is like my favorite math.
F of x is a fancy way of just saying y equals, right? So don't worry about that for now. This is what we did. We started at 0. 0 was the initial value because it was our y-intercept. Our y-intercept and initial value are the same thing. Let me go ahead and label that in our graph as well. This is what's known as the y-intercept. It's also known as the initial value. We started at 1. We started at 1 in our table and then multiply by 2, multiply by 2, multiply by 2, like we do here forever and ever. That's what happened.
Oh.
I talked about this on Tuesday. What is the shortcut with a quiet raised hand for repeated multiplication? Oh, look at all of you. Let's go with Cody. He wasn't even here on Tuesday. What is it?
He knows the definition, but not the
I know
word.
what it is, but yeah.
It's an exponent. Yeah, the number up there in the top right, right? So if I start with 1, if I want to do multiple copies of 2, I do 2 to a power. If I don't know how many 2s there are, make it a variable. Do you want to have 3 copies of 2, 4 copies of 2? Plug that number into the variable. A variable is just a holding container that can hold anything at once. So it's 1 times 2 to the power of x. That's it. There it is. That is an exponential function. And notice what it has. It has a variable in the exponent. Therefore, we call it the exponential function because it's an exponent. So I'll say variable in the exponent. So more generally, we can have any initial value that we want. It doesn't have to be 1. This will always be the y-intercept. So in this case right here, the y-intercept was 1. So in general, an equation for a function that is an exponential function will be f of x is equal to some number that is the y-intercept or the initial value times another number that you're multiplying by over and over again to the power of x. Again, this a is the y-intercept, or it's the initial value, and this b is the thing that we are multiplying over and over. In this case, we were multiplying over and over by 2, so I had a base of 2. This is a base of b, and it can be anything that you want to multiply by. I'll call that, for now, colloquially as the multiplier, but there's a more technical name later. Maybe I'll just teach that now. I'm going to call this the multiplier. But textbooks will not call it a multiplier. Textbooks will call this something else. They'll call it either the base, which is not very helpful, or the common multiple, which is a lot more helpful, or a common ratio. I prefer common ratio, so I'll say common ratio. It's a thing that we multiply by over and over again. So another 2 things before I go to some example problems. How am I doing on time? I still have time. If I'm talking about an exponential growth equation versus exponential decay. Have you guys ever heard the word decay? Raise your hand. Decay. Rings a bell? Yeah, tooth decay. Things that go down, things that are bad, right? And then exponential growth, things that grow out of control. If you think about what would be a good example? You guys know, what was that radioactive disaster?
Black Plague.
No, what was the one in Fukushima?
Mercury.
Anyway.
What's it called?
Okay, the plague is exponential growth too, but
Yes.
I was thinking about that one. There's 3 Mile Island. There's a bunch of famous ones. Those all had unprecedented levels of exponential growth, and it was so fast that it literally exploded. And that's literally what the explosion is. It got so hot that it made the water turn into steam so fast that that steam was literally an explosion. And that's usually what destroys nuclear power plants. It's the steam that rapidly heats, expands like at an exponential rate, and that exponential rate is interpreted as an explosion. Go ahead and don't do that. All right. So let's talk about a table value. Put it down. Put it away. So if I have a table where I'm just going to do 1, 2, and 3 and be lazy, an exponential growth will have something that looks like this: 2, 4, 8. However, exponential decay will have something that looks like this: 1, 2, 3, but 8, 4, 2. Notice that on a table, exponential growth goes up, it gets bigger, and exponential decay gets smaller. Which means if I do the analysis on this, what am I multiplying at each step? Multiply by 2, multiply by 2. What about over here? It's not multiplying by 2 anymore.
Multiply by 1/2.
Yeah, so you're kind of like dividing or multiplying by that fraction of 1/2. So decay is when you're multiplying by a fraction or a decimal that is between 0 and 1, or a small value. Why is 1 the boundary? That's a more advanced question, but if you multiply by 1, does it change? Multiply by 1, multiply by 1. 1 is the boundary point because when you multiply by 1, nothing changes. If you multiply by a number slightly bigger than 1, like 1.01, it'll be exponential growth. If you multiply by a number slightly smaller than 1, then it's going to be like 0.99. It'll be exponential decay because multiply by 1 doesn't do anything. Yes, question.
Like, for the other one, the limit thing is like 0, past 0.
Yeah.
Not the past 0.
That's a great question. Let's answer that right now. So let's do the first half. Exponential growth, we've already seen an example of that. Let me make a quick sketch. So on the right side, it shoots off to infinity. On the left side, it goes through the y-axis, and then it gets closer and closer and closer and closer and closer to 0. It's the opposite now. This one shoots off the charts up here, and then it goes through the y-axis and gets closer and closer and closer and closer to that y-axis. It's kind of a reflection over that y-axis, flipping it left and right. Okay, and then for the equation, it's going to have the same exact equation. It's going to be a times a number to the power of x, and this is going to be a times a number to the power of x. The only thing that's important here is what sort of number we have here. If I have a number that's slightly bigger than 1, like 1.01, it'll be exponential growth, and a number that's slightly less than 1, like 0.99, that will be exponential decay. I will note here, when I say big values in exponential functions, that just means bigger than 1. If I say small values, that doesn't only mean less than 1, it also means greater than 0. If you try to if you multiply by 1, it's a straight line, it doesn't move. If you multiply by a negative, what happens if I multiply -1 times -1? And if I multiply by -1 again?
Negative.
And if I multiply by -1 again, it jumps up and down and up and down, and that graph is too weird to analyze. I'm going to assume that the base is always positive. Whew! We just did an insane amount of learning, all
What
three
the
categories of exponential functions, and now I'm going to show you how you can apply those things. Whew, here we go.
There's so many steps.
These are the problems that you can try on your own. I'm going to be giving you some checking your understanding problems tonight. If you want to do some problems on your own that were like the old-fashioned homework, these are the problems that you should practice, and these are the problems that I can help you with that practice. You do not get extra credit from the class, but you get extra credit in your soul. So in number 1, are these tables modeled by an exponential function? Notice that for our inputs, we can kind of ignore the inputs as long as they're constantly going up. This one is adding 2, adding 2, adding 2. This one is adding 10, adding 10, adding 10. Typically speaking, in all of this unit, you kind of ignore the x's. You don't really care that much about them. What you really care about are the y coordinates. What are you doing to get from 3 to 6, to get from 6 to 9, and 9 to 12?
Add 3.
Who are we adding 3 or multiplying by 3?
Adding
What are we
3.
doing?
Adding.
If 6 is being multiplied by 3, it would have gone to 18. So this one is adding 3, adding 3, adding 3. So the simple answer is no, it's not exponential. Let me take it a step further. What was this one? Linear. Very good. All right, what about this next one? How do I get from 60 to 30, 30 to 15, 15 to 7.5? Times by 1/2, times by 1/2, times by 1/2. So let me ask the question again. Can this be modeled by an exponential function? Yay or nay?
Yay.
Yay. This one is a no. Oh, let me write it in pen. This one is no, and this one is a yes. That's the only thing that you really need to answer for those questions, analyzing if it's adding by the same number and multiplying by the same number. By the way, I've said it before, and I will say it again. If you, guys, if you accidentally multiply by a different number, if I multiply by 1, multiply by 2, multiply by 3, if these are not all the same number, then it's not exponential. It's some other weird type of function that we can talk about later. To be exponential, it has to be the same number over and over again. Otherwise, I can't use this trick where I do the same number to the power of x. Remember, this power of x means I have the same number, same number, same number. That's our shortcut for repeatedly multiplying by the same number. All right.
1/2 to the power of 3.
1/2 to the power of 3 is 1 to the power of 3 over 2 to the power of 3, which is 1 over 8, so 1/8. Yeah. All right, so for each of these functions, I want to sketch its graph. And when I say the word sketch, I do not need to have x and y coordinates on there. I don't need to know this is 1, 2. I just need to know the general shape. Does it look like this, or maybe there's some other options that we might have to look at. And then we're going to state what the y-intercept is, which is really easy. It's going to be that number out in front, the domain, the range, and a equation of the asymptote. The equation of the asymptote is always going to be y equal to a number. So a bunch of easy things to analyze. Let's go with number 3. Okay, first, let's do a sketch. This sketch is going to look like what? Is it going to be exponential growth or exponential decay?
Exponential decay.
Why?
Because it's multiplied by a fraction and go down.
Yeah, so this one is decay. Look at the base. It's going down. So here's my sketch. My sketch is going to look like this. And technically, it should not touch the x-axis, but if I zoomed in there, maybe it doesn't touch. So there's my sketch. I need to state what the y-intercept is. The y-intercept is what? Someone other than Henry. 4. Why, Ivan?
Because it's the number right there.
It's the number right there. That number is always the y-intercept. Easy peasy, lemon squeezy. All right. Next, we have domain. For domain, I'm just going to do a capital D. What is always the domain of an exponential function? What am I allowed to plug in to go left and right on my graph? Everything. I do a capital R with bold. The range is going to be a little bit different.
The limit is 0 and infinity.
0 to infinity. There it is. And finally, the asymptote's equation is going to be y equals.
4.
Where is that asymptote, that magnetic force that you're not allowed to touch?
0.
Y equals 0.
Is it 0 for all the
It's 0 for most of them, not for this one.
for that one it's what?
Close. It's -1.
Positive 1.
All right, very quickly, number 4. Is this exponential growth or decay?
Decay.
I hear decay. I hear growth. Give me thumbs up, growth, thumbs down, decay. Look at that base underneath the X. Is it bigger than 1 or less than 1? Bigger than 1 means growth. So let me do a sketch of growth. Growth looks like that. All right, what's the y-intercept? Oh, there is no number. Oh no, what do we do?
We have to run away.
Oh, is
We
it
have to
one?
run away.
It's 1. Why, Leo?
Because 1
Six
times
divided-
anything, 5 just.
Oh, I was.
Yeah, and technically I should be writing 0, 4, and technically I should be writing 0, 1 because it's a point on the plane. Yes, it's 0, 1 because this 1 right here is invisible. When you multiply by 1, it goes away. That's where it went. Cool. All right, let's keep going. The domain for this thing is what? All real numbers, easy peasy. The range, again, is the same thing, 0 to infinity. And our asymptote is y equals 0. Okay, these things are going to start to change on you. Be careful. Here comes the change up. All right, let's graph this one. Is this exponential growth or decay?
What? Hold on. Decay.
Yeah,
No, I
decay.
didn't see
The,
the.
oh,
Decay.
decay.
I didn't see the negative.
So this number indicates that it's growth, but this number means that there's negative values. If you plotted all the x and y coordinates, you would notice that every single y coordinate, this is always positive. A positive times an always negative is an always negative. This one, it lives not on the upper part of the graph, but on the bottom part of the graph. And then you have to figure out, when I move to the right, am I going away from the x-axis or towards the x-axis? Because this number is big, it's moving away from the x-axis, and here's your sketch. It's like an exponential growth equation that got flipped because that leading coefficient was negative. All right, our y-intercept is a little bit tricky, but you guys can get it. Y is equal to, or y-intercept is, it's 0, -7. Good. What is the domain? The domain is the same thing every single time. I'll never trick that. All real numbers. The range on this one is
Negative infinity.
2.
0.
There it is.
Yes,
From
we
negative
got it.
infinity all the way to 0. And finally, the asymptote is still y equals 0. All right. And number 6 is the trickiest type of problem I can throw at you. Ready, set, graph.
What?
All right. This number is positive. We don't have to worry about it then. If it's negative, it flips it. I'll write that down just in case you forgot. This means
But it is decay, though, right?
flip over x-axis. This one is not flipping over the x-axis. This means decay, and this one shifts the entire function down 1. So watch this. The asymptote used to be this value right here. That is no longer the asymptote. The asymptote also got shifted down 1. There's the asymptote now, and you have an exponential decay function that looks like this. Oh, I didn't mean to do a dash line. Let's do a solid line.
What the heck?
What the skip?
All right, be careful here now. The y-intercept is not 27. The y-intercept now is
Negative.
26. Why?
Because it goes down 1 and then the y.
Oh.
It used to be 27 until we subtracted
What?
1. Very good. Yes, it's 0, 26. All right, the domain is always the same value. It's always all real numbers. The range here is going to be tricky. Let's see if you guys can get it. Well, negative infinity implies it's down here, right?
Oh no, then it means
Negative 1 to positive infinity. Very good. And finally, the equation of this blue dash line. Negative 1. Whew. Look at all that math that we just did.
I like that.
How am I supposed to do a student example?
On a student example, you can make yourself a table, just make up an equation and do the analysis. I have a question for you guys. If you want, my question is this. If I have the following table, this would be a great student example. In the following table, I have x values and y values. If I go, I'm just going to go 1, 2, etc. And my values are 3 and 6. Is this exponential, or sorry, is this an exponential or is it something else?
Is it gotta be
No,
times
no, no,
that?
no,
no.
Plus three.
Yeah.
It's linear.
So it can be both, multiplied by 2 or
You need to see the rest of the whatever.
Yeah.
Unknown.
Everyone, give yourself a pat on the back. With 2 points, it's unknown. I could be adding or multiplying until I have a third point. I can't confirm
Can
nor
that be
deny.
an example?
If you want to make that your own, you have my permission and my blessing. That does include the lesson. Oh, good job, guys.
I don't know